Thank you everyone for being here. It's a pleasure to be hearing about so much about black holes. Although I was telling someone here yesterday that it's amazing to hear so much about black holes as they are being observed from gravitational waves. And we heard Adam gave a very nice introduction for what I'm going to talk about in this presentation, which is the connection from stars to their black holes. And it's a bit frightening in many ways how little we know about that connection observationally, and hopefully I'm going to sort of motivate some of that. Also, I think I might be one of the few transient observers in this audience, which is great because I will tell you about how transient observations alone, it's remarkably difficult to infer when a black hole does form, and why we've had to push to really unconventional techniques when it comes to the transient landscape to understand what might be happening. So as far as I can tell, all of us, we are talking about black holes, we think about black holes, what stars are forming black holes, but really the situation looks something like this, where the big elephant in the room is what stars form black holes. And just if you're wondering, this is what ChatGPT creates when you ask it to create a space elephant in the room. All right. So I'm going to start off with a question that I think is on all our minds, which is what stars form black holes. And just to sort of start off the discussion, I like showing this plot, which is probably incorrect in many, many ways. This is what I've taught this plot in graduate courses and high energy astrophysics because it was taken for granted that this is how the universe works, which is that if you stars above a certain mass, they stop exploding as supernovae, they don't turn into neutron stars, and they undergo the so-called fallback to form black holes. But as we heard from Adam yesterday, and you've probably seen in the literature, this picture is becoming a lot more and more complicated as the simulations improve. And if you look at the latest state of the art, this is sort of a popular way of showing how complicated this landscape might be, which shows that depending on what mass you're at, you could get a successful explosion, which are the green bars here, or you could get a failed explosion. And depending on which model you use, what stellar evolution code you use, you get completely different answers. So it's a very, very messy landscape, even as far as the theory is concerned. And I think one of the primary limitations has been that observationally, it's extremely difficult to infer when a black hole does form in a stellar explosion. So Adam told us yesterday about these so-called silent supernovae, stars that purely implode and do not produce an observable transient. So just want to make sure I want to revisit some of that and remind all of us what that scenario actually looks like. So even though we call it the so-called fallback channel, where you have a star that essentially falls back into itself and forms a black hole, it's by no means silent as such, and this has been predicted for a very long time. The picture here is that even if you start with a massive star that has a helium core and a hydrogen, huge hydrogen envelope around it, even if this star were destined to turn into a black hole, you would expect the core to first collapse into a proto-neutron star. This is something you expect in any black hole formation scenario. And as this core radiates away roughly of the order of 0.1 solar masses worth of neutrinos in energy, this essentially suddenly the outer envelope feels 0.1 solar masses less of gravitational attraction in the center. What that means is that this is something that was predicted, theorized back in the 70s, which is that just this pure loss of mass in neutrinos is enough to make the outer hydrogen envelope suddenly feel the lack of this gravity in the core, which will likely eject it with explosion energies of the order of 10 to the 48 ergs. So again, in this case, the star itself is not actually exploding. It's only the outer hydrogen envelope that does not feel the gravity of the inner core anymore, so it gets ejected. And these could lead to explosive transients, albeit these will be low luminosity transients. This is something that Lovegrove and Woosley worked out almost more than 10 years ago, which is that you would get these roughly 10 to the 48 erg low energy type 2 supernovae, and eventually this low energy outflow as it goes out and expands, we're talking about just the very outer hydrogen envelope of the star. This would likely cool enough to form dust, and these would become essentially infrared transients at some point. And this is something that, again, was worked out more than 10 years ago, which is that these low energy outflows would lead to dust formation and produce these dusty transients from the birth of these black holes. So this naturally has motivated observationally a lot of searches for these things, because what you're looking for in these cases is a fairly low energy transient which may or may not be observed depending on your sensitivity. But what you would expect is that you would expect these stars to randomly disappear, and you'd see really luminous massive stars that disappear into darkness. And there have been a number of searches looking for these things, and I'll come back to this. But I really wanted to highlight why this is so difficult observationally. Why is it so difficult to find individual stars disappear? So I pulled up this movie from the internet last night. So what you see here is a very famous galaxy, NGC 6946. These are two images taken roughly 12 years apart. I think one was 2005, one was 2017. There are actually two stars in this galaxy that have, in between these epochs, which have died. Does anyone see at least one of the stars that has died? See in the supernova? That's SN 2017 EAW. This is a very bright, well-known supernova that exploded in 2017. Turns out there is one more star that has died in this galaxy. Which one? I didn't even spot where it was. Yeah. Anyway, I know it's actually not in the. It's actually in the disk of the galaxy. Right. So what I'm trying to get at is that in order.
Is disappearing and dying the same?
Well, there's an interpretation which we'll come to in a bit, but essentially what you would expect is that you have a luminous supergiant that abruptly disappears in the galaxy if it was collapsing into a black hole. So the thing that I'm alluding to, especially for folks who don't think of observations, is that it's remarkably difficult to see individual stars disappearing in nearby galaxies. If you have a supernova, that's great. The supernova outshines the entire galaxy for a few weeks. But if you have something that doesn't quite do that, it's very difficult to tell when a star disappears. So the only reason we know that the other star died in this galaxy is because of this survey that was led out of Ohio State with a large binocular telescope, where what they did was that they were looking at these nearby galaxies, doing pointed observations, creating light curves of millions of supergiants, trying to look for stars that disappear. And this is probably what you've heard of when you think of these failed supernovae. And this is this star. It's called, it's been, well, at the time it was already called NGC 6946 BH1, where what you see is this roughly 15-year-long light curve of this star going all the way back to 2000. It had this brightening that occurred around, this brightening that occurred around 2009 or 2010, had this faint outburst, and then it completely disappeared. So the main thing that you see over here is that there is this faint optical transient that was flagged as part of this monitoring campaign. This was a very luminous supergiant, as you can tell, 10 to the 5 solar luminosities. And then you have this faint infrared brightening that also accompanied, and then it continued to fade away. It really, plummeted in the optical, so it's not there anymore, but you see there is this faint infrared glow. And there's follow-up HST imaging of what this star looked like. You see on the top, this is what the progenitor looked like, I think, back in 2005. And this was re-observed in 2015. You see the star disappeared over this time. Okay. So this obviously, was a very promising candidate for this so-called class of explosions. I think one of the first really convincing ones that came out. Turns out that there've been a lot of recent discussion and tensions about what this actually is, especially after JWST came online. This is actually a JWST image of the remnant from about a couple of years ago. What you see here is that there's still a very luminous infrared source at that position. So even though the source has disappeared in the optical, there is still a lingering infrared source over there, which is, begs the question, what is this thing? But it turns out that this is the SED of that source compared to its progenitor. So the dashed line here is the progenitor star. And you see what the remnant looks like today. It's a very dusty, obscured source. And the main point is that the luminosity of the source today is actually much, much fainter than what the progenitor was. About 15% the progenitor, the luminosity of the progenitor, even if you account for all the infrared emission that we see from this object. So, couple of years ago, maybe actually last year, there was a lot of noise about, why is this source still there if it's actually collapsed into a black hole? And, there were claims that maybe this is not a failed supernova. But what I'm going to claim, and I'll show you later in this talk, is that I think a lot of this was because there was a lack of coherent theoretical models that pulled together all of the different things that are happening in this process. And what I'll try to show you is that if you put together all of the different physics that we can learn from these observations, you actually do get a coherent picture. And a lot of it is driven by the identification of one new object, which is quite remarkable, that has allowed us to really put together a consistent story. Okay, so coming to sort of the new object that I was talking about, turns out that many of you would not have sort of probably thought of this as a transient survey. So for those of you who were sitting at home in 2020, turns out that there was this really bright comet that passed through the inner solar system. It was called Comet Neowise. It was made the headlines on New York Times, how to see the comet Neowise. So for those of you wondering why was it called Comet Neowise? It was because it was discovered by a survey that's called Neowise. So Neowise is not something that we usually think of in the transient community because it is not a transient survey. Neowise is this NASA mission that was launched in 2009, and what's been doing for the past 15 years until it was decommissioned last year was that it had this orbit around the Earth, which was always around the day-night terminator. And as you keep doing that over time, what you can imagine is that every 6 months, you come back to the same part of the sky. And what you're doing is every 6 months, you're creating a full mid-infrared map of the sky. And this essentially allows you to get time domain information. And in fact, if you look at this comet itself, you see this red thing moving across the sky. That's actually those are the discovery images of the comet itself, which is why Neowise was funded by the Planetary Astrophysics Division to make measurements of these solar system objects. So a few years ago, when I was starting my postdoc, I thought, this is like, sure, you can find moving objects in this thing, but what you're doing at the same time is creating a movie of the entire sky in the mid-infrared. So not only do you see things that are moving over the sky, you also see static things, but changing as a function of time. These are Neowise images of a bunch of random stars in the sky. What you see here is that you see a lot of really interesting variability that you see, except that this is from the Neowise survey, and this is in the mid-infrared bands, which are almost impossible to observe from the ground. So what you can do is that you can take all of these images, which are roughly of the order of 1 million images taken over 15 years, and essentially transform this into a transient survey if you just apply the same image processing techniques that we do for ground-based surveys. And that's what we did, which is that this is sort of bread and butter for us transient observers. You take, on the left is what you call a science image, a new image of the sky taken, let's say, last year. You can take the same part of the sky taken 10 years before, you subtract the two, and you see things that pop out, which are things that have changed in the sky. This is what we do with image subtraction. And you can do that to create essentially light curves, 15-year-long baseline light curves of any source you like in the sky. Now, the catch is this, which is that even though this looks like a really beautiful light curve, just keep in mind that this is 15 years, and the cadence is 6 months. 6-month cadence is not really something that would get transient observers excited, per se. Because, I would like 6-hour cadence, but this is 6-month cadence. But what we realized a few years ago was that because of the long baseline, and because we are looking in the mid-infrared, where there's basically no transient survey capability in the mid-infrared, even with this long baseline, you could make lots of discoveries that were sort of not being seen by your conventional optical ground-based survey. So that's sort of what led to this identification. And I won't get time to talk about the rich landscape of discoveries, but I'll show you at the end what we're finding. So we had a program to look for these luminous infrared transients in nearby galaxies, again, with this 6-month cadence data. I'm showing you how that works, which is you see a bunch of these nearby galaxies, and when you do the same, before-after subtraction, you see there are point sources that stick out on top of galaxies. This is, again, something that you can do uniquely with image subtraction. And these are, some form of dusty supernovae, dusty transients of one form or another. And we essentially did this for millions of sources in Neowise, trying to look for objects that were of, worthy of follow-up. And as far as the topic of this talk is concerned, turns out that one of the first remarkable objects that came out of this search was that we just had to look at this galaxy, which is, hopefully everybody recognizes, this is M31. This is our nearest Milky Way-like neighbor. And right here, in the disk of M31, something flared around 2015. You see there's this bunch of 3 stars that you see right next to each other. And you do the same image subtraction process. You see the top star in that triplet brightened in 2015, and that flagged our pipeline saying, hey, something happened over here. And we had this huge ground-based program using NASA Keck time, Magellan, and everything to get spectra of things like this that were burbling in the infrared and trying to understand what these were. And this is where sort of, I think, at least one of the most shocking moments in my life came about, which is that I had this program on Keck. I remember I was in Hawaii observing this source. So what you do in these cases is that you take a finder chart, which is an archival image of that part of the sky, see the same 3 stars that we were seeing earlier. The top star is the one that we were interested in. This is the star that we wanted to get a spectrum of. I was like, sure, we'll point Keck at it, and we'll point Keck, we'll see the star, we'll get a spectrum, and we'll understand what this is. Turns out that I was observing at Keck, and I was like, 1, 2, 3. You see the bright stars, 1, 2, 3. There's nothing there. And for those of you who don't, many of you don't observe, but this, oops, no, see, even this disappeared. Yes, there we go. Yes, very timely. I did not plan that. So you see that I was trying to, it was like 4 in the morning. I had no idea if my brain was functioning or not. But you see that, I was trying to get a spectrum of this source that was not there. And if you don't see something with the largest telescope on the ground, it's really something weird going on. These stars don't disappear like that. Because 2MASS is not a very deep survey. It's a much, much smaller than Keck. Okay, so because this is M31, turns out that a lot of the work, the observational data that we needed to make the interpretation was actually already there in the archives. We didn't even have to get any follow-up observations. HST had some beautiful imaging of the location. What you see here is this source that is almost borderline saturated in HST data. This is just, this was just there in the archives. We didn't get any follow-up observations because people have been monitoring M31 for many other reasons. This is that source over there. And so these are images from before the star disappeared, had the infrared brightening. And this is from, I think, early 2010s. And we could pull together all of the light curves we could lay our hands on, Y, span stars, ZTF, PTF, you name it. And you could put together this beautiful light curve which spans optical to mid-infrared light. You see the top panel, the orange and black points, those are the Y's light curves, 6-month cadence, very slow. But you see it sort of burped in the mid-infrared around 2017, and then it disappeared, slowly faded away. And it did something even more remarkable in the optical, where it was this sort of slowly varying this star that eventually plummeted in the optical, and it's nowhere to be seen today. Again, this alone, I would not be as convinced, like, yeah, I don't know, it's like you don't see it in the ground-based survey, so what? Turns out that, again, we had serendipitous HST data, again, from after the star disappeared, because somebody else looked at the galaxy again for unrelated reasons. And you see, these are the same part of the sky seen with HST after the source disappeared, and you see it's not there. So before, after, the 2 sides, you see the source has disappeared. Now, that's the thing. If something is not seen in HST, it's really not there. We're talking about limits of the order of 28th magnitude. It's about as faint as you could go with optical light, with state-of-the-art technology. Now, to be honest, I was terrified for many weeks when I found this, and I know that, for those of us who don't observe, it's not obvious why this is terrifying, but I wanted to give you an example of what this means. So imagine, we're now in the winter season. If you go out at night, at midnight, you look up towards the eastern horizon, and you'll see a bunch of stars in the sky. Imagine you went out tonight, you're looking at the sky, and this is what the sky looks like. Is there anything weird about the way the sky looks like right now? Yes. Betelgeuse has disappeared. This is essentially what this means, which is that we have the nearest Milky Way-like galaxy has a supergiant that disappeared, and nobody noticed for 5 years. As transient observers, we like to think that we have a complete inventory of nearby core collapse supernovae, the so-called massive stellar deaths. And this star disappeared and nobody noticed for 5 years. So this is equivalent to seeing this. Like, you imagine you wake up at night and like, Betelgeuse is not there. hopefully we would notice this, even if we don't see stars in M31 disappearing. Okay. So back to the basics. This obviously started off this entire chain of understanding what this thing was. Obviously, we had our first suspicion, like, this smells like one of these objects that were supposed to occur when these so-called pure implosions happen. So because this was again in M31, we had this beautiful SED of what the progenitor looked like, all the way from the ultraviolet band to the mid-infrared with Spitzer. You can take this SED and fit your favorite star plus dust shell model. Turns out you do need a dust shell to explain the mid-infrared excess around around 10 to 20 microns. And this star has been recorded in catalogs since the 1970s. Again, people have been staring at M31 forever. So we know that this star had been around for a very long time. So what you can do is that with this model, you can measure what the temperature, the surface temperature of the star is if you take the dust and the photospheric model together. And you put that on a HR diagram, log L, log T. This is what that looks like. So what I'm showing here is a HR diagram with a bunch of missed stellar tracks. These are single star tracks. And what you see is that if you put that on this plot, this source on this plot, which we are calling by this name, turns out that it's definitely a supergiant. It's 10 to the 5 solar luminosities. Turns out that it's not quite on the red supergiant track yet. It's actually a bit bluer than that. So this is what in stellar populations, this is what you would call a yellow supergiant, not quite a red supergiant. And I think the most reliable parameters you can draw from this measurement is that the luminosity is about log L of 5, temperature is about 4500 Kelvin, and if you take the luminosity alone, this gives you a helium core mass of about 5 solar masses. That's what gives you this luminosity. So if you're thinking of what this corresponds to, we created a bunch of models in MISA, not me, this is actually Morgan McLeod, my collaborator. He created these models where you start with a 13 solar mass object, you crank up the mass loss rate at the end of its life. So this is kind of the picture that we are getting at, which is you have a 5 solar mass helium core, you have roughly a thin hydrogen envelope around it, it's mostly stripped, and basically we get these conclusions from taking the blue color of the star, which requires the star to be stripped to some extent. And we know there is a dusty wind around the star because we have this mid-infrared excess around the source. So these are all really just derived from observations. We are not really just playing with parameters or something. We actually measure these parameters. So this is what the progenitor star looked like. And fast forward to 2022, turns out that this source turned from being this blue luminous supergiant to this very dust obscure source. You see, in the optical, it has plummeted by a factor of 10,000 in optical luminosity, so it's really not there. And it's still there in the mid-infrared, and we can fit our favorite dust model to it again. Turns out that when you do this calculation, there are 3 things that you can derive fairly reliably. One is that this source is fading, it's disappearing, and it's currently faded to less than 10% of what the progenitor was, so it's already gone. And this is what leads us to believe that the star is really not there anymore. Whatever was powering the central luminosity source, 10 to the 5 solar luminosities, it's really not there in the center of the star anymore. What we can tell is that there is, because we have beautiful coverage of M31, it's the nearest Milky Way-like galaxy from, and we have coverage of it from time domain surveys, there's no evidence for any explosive transient to a limit which is of the order of the progenitor luminosity. Over time, as the star has disappeared, this really means that the outer layers of the star have condensed into dust, and that's what produces the dust obscuration around the source. Okay, so if you put all of these things together, it turns out that you can construct a very beautiful story, which is that this does appear to be an example of a star dying with what looks like essentially a textbook implosion, where you have a star that looked like this, that likely turned into a compact object at its center, has to be a black hole given the mass of the object. And here is where some of the new theoretical insights came in, just because we have this beautiful data set on this object. The first one being that if you just take the star and let it fall back on itself, turns out that the pure gravitational pre-fallback time is of the order of 6 months. But we definitely see this source hang around for a much longer, so not just plummeting back into the central object. And the three key things that we had to put together is really that we expect that this neutrino mass loss shock, which comes from just from the loss of neutrinos, likely puffs up the outer layer of the star, so that the outer layers of the star are asymptotically unbound because of the energy that's put into it, and that the fallback into the black hole likely generates some luminosity, which you can, to first order, you can guess that it scales with the mass accretion rate onto the object. And then that not only is the star falling back, but work by Elliott Quartet, Andrea Antoni have been showing that the fallback is somewhat restricted because of the random convective motions in the outer envelope. So what you're really looking at is that this object is trying to fall back. There is convection in the outer layers. It's not really able to fall back because of this the random angular momentum. And if you take all of that, we can create a bolometric luminosity light curve of this source. It's beautifully sampled because this is M31. You see it starts off with this fairly constant luminosity in the early days, and then it just starts dropping and essentially follows a power law at late times, where you see this source disappearing away with time. And all of these can be fairly well explained with a hydrogen depleted roughly of the order of 0.1 solar masses, depending on exactly what stellar model you assume, but an explosion energy that is less than about 10 to the 48 ergs, 10 to the 48 ergs. Okay, so I told you I will come back. Yes, thank you. I will come back to this object because we have such beautiful data on this object, because this is so nearby. We can actually revisit some of the claims that were made for this object and really try to create a model that explains both objects, and we think we have one. So it turns out that if you take that same HR diagram plot, our source is over here in M31. Even NGC 6946 is slightly above that. It's a more luminous source. It actually, I think, the luminosity of that source is like log L of 5.25 or something. So in the original paper, it was suggested that that source was actually a red supergiant, which would mean it's a much more puffed up star. But you can almost tell over here that the best fit model actually is not quite at a red supergiant. It's actually slightly bluer than that as well. So this actually, the best fit model for that star too also looks like a yellow supergiant. And in fact, this is something that was suggested many years ago, which is that this paper by Humphreys in 2019 showed that the SED of the source was much better fit with a yellow supergiant than a red supergiant. And we ran, again, sort of a similar infrastructure for this source. Turns out that you can come up with these parameters, which is roughly about log L of 5.3, which corresponds to a helium core mass of about 7.5 solar masses. And you repeat the entire infrastructure again for this source, run our model for this source. Turns out that you can very nicely explain why this source is fading so slowly with time. Because this same set of processes, which is the neutrino shock, the convective motions, which hold back the fallback, you see that this is the green dots are the luminosity of this source measured as a function of time. You see it continues to essentially follow that power law. And essentially the prediction of this model is that this will continue to fade into darkness over time. This will, this is not some other type of object. This is actually something that has formed a black hole and will continue to fade into darkness as this dust obscured source. This was what we said in the paper. Turns out that a few months ago we got JWST data on the M31 object because it's so nearby. So this is this M31 source seen in JWST, also a bright mid-infrared source, no surprise. But what we were predicting in the model was that this source also will continue to fade over time as it just disappears into darkness, as the black hole sort of slowly eats up the star. And there you go. So we have the progenitor luminosity, which is the dashed line. This is the black solid dots are what we saw from the WISE data in 2022. And these are the colored plot lines that you see over here. These are the JWST data from a few months ago, which show that this source is continuing to fade away and becoming more and more dust obscured with time. And today it's about 5% the progenitor luminosity. So it's really continuing to fade away. So, the prediction is that even the other object will continue to do this. All right, so this is my last slide. What I'll say is that, obviously we heard a lot about, seen plots like this yesterday during the talks. Also, Adam mentioned this, which is that, there is this expectation that stars in some mass range turn into black holes. This one, as I said, is a 13 solar mass star from our models. Maybe you can come up with a slightly different model that produces a slightly different number. But the point is that if you put both of these two objects on this plot, Turns out that this NGC 6946 object actually fits very well with this so-called compactness peak, because it's a slightly more massive star. This object, though, it's slightly too less massive to turn into a black hole, which, data is data. I'm not going to say which model is wrong, but, this is what we are seeing. And, I'll show Adam's plot again, which is that Adam also mentioned yesterday how there is this weird range of 12 to 15 solar masses, where historically nobody expected to find black holes. We actually see stars in this mass range now that are disappearing into things that are likely black holes. So this is, again, something food for thought for the theorists, and I think with observations, you're starting to connect some of these dots. All right, so this is my last slide. I'll just say that the WISE project has led to a remarkable number of surprising discoveries. I will obviously not get to talk about it, but some of this, I think, is of interest for this audience as well. Things like CSM shells around massive stars. We can see them in WISE. But it's really been, I think, an unsung hero for time domain astrophysics, the amount of stuff you can do with this very long baseline mid-infrared coverage of the full sky. Thank you.
Let's see. Salvo.
Thank you. Great to see this. Quick question. Would the M31 object be close enough that we would have any hope to get any of this 0.1 solar mass of neutrinos with the ice cube or something else? Have you looked?
It's a very good question. So when we announced this paper on the archive, we heard from the Super Kamiokande team. And turns out that just 2 weeks ago, they actually put out a paper on the archive where they looked in this direction. Turns out that the biggest uncertainty for this object is that if I go back to that light curve, unlike the other object that in NGC 6946, this one doesn't really have a clear time when the star collapsed. It's like, it's sort of slowly disappeared over a few years. And that actually introduces some, like, they don't exactly know, they know where to look, but not when to look exactly. And that, I think, reduces the sensitivity of the search. But they looked and they didn't find anything. Turns out that they were able to rule out one very optimistic neutrino model to be able to do this. Yeah.
Okay, yeah, the yellow supergiant scenario.
Yes.
How good are the SEDs that you use to come to that conclusion? And could it be consistent with a slightly fainter red supergiant plus an O star or something like that?
Plus an O star. So, I think the main thing here is that because we have this mid-infrared coverage from Spitzer, or to 25 microns, you need some optical depth in the shell to be able to explain why there is that excess. And if you fold in that optical depth, you have to make the photosphere a bit bluer to fit the optical SED as well. So I think that's what the constraint is, which is that because I don't think the O star scenario works because this is a 10 to the 5 solar luminosity giant. And unless the O star was also becoming a supergiant at the same time, it would be difficult to imagine why the companion is also like, similarly luminous to contribute to the SED.
Okay.
Hans-Walter Rix, wonderful stuff. Quick question. Does LSST Rubin, will it do anything for that field, or are all the interesting spots in the 100 nearby galaxies that the OSU survey has looked at anyway?
No, that's the funny thing, which is that if you look at the OSU survey paper, they said we will look at all 100 nearby galaxies except M31 because it's too nearby and it's too big on the sky. And that's where we found this object. It's a bit surprising. But yeah, so I think if just by numbers itself, LSST will detect individual supergiants out to 50 megaparsecs or so. That's the rough number. But I think the constraint is going to be confusion for ground-based images, like being able to, I think even today, and I tell this to my colleagues in transients, that nobody actually looks at the negative alerts that come out of surveys because everybody's looking for exploding stuff. But transient surveys, including LSST, will look for negative things disappearing from the reference image as well. I think that's what we would need. But on paper, it is 50 megaparsec, but I'm not as optimistic as that because of confusion.
Hey, very nice results and talk. Thank you very much. About your yellow supergiant scenario, especially for the one candidate you mentioned, you had a model with about 5 solar masses for the yellow supergiant,
yes,
but an initial mass of roughly 20?
13.
30 even?
Yeah,
okay,
yes,
so somehow the 30 solar mass star needs to lose 25 solar masses?
No, not 30, 13.
13, okay,
yes,
sorry.
Yes, yes.
So somehow the star needs to lose about half its mass. That's still an appreciable amount.
Right.
It's at odds, I would say, with standard mass loss of progenitors. So my question is, do you think there could be a companion star in there, and could you say anything about that?
No, that's a great question. I think, so sort of going back to this cartoon that I was showing, turns out that you can measure the terminal mass loss rate of the star, and that essentially comes from this, the red part of the SED, which shows the dust. So the dust is a good indicator of how much wind there is, and those numbers themselves produce a mass loss rate of about 10 to the minus 4. And that's quite high for supergiants, but this is something we can measure from the data without much assumptions. So yeah, so what we did to get to a 5 solar mass from 13 solar masses is to just let this 10 to the minus 4 solar masses run for the last 10,000 years or whatever, something like that. So that's what we did in the MESA model, which was motivated by the observations. Now you can ask whether this is induced by a binary companion. And we did this calculation. Turns out that I think if the source was isolated, because this is HST and M31, we would be able to see like even sun-like stars as companions. But I think I think that if there is a companion, this is currently inside the dust shell. It's probably very nearby.
Norbert Langer, yeah, that's beautiful work.
Thank
Fascinating. I still want to challenge you by proposing an alternative model and see what you say. What if, the star had the envelope you say and just threw off this envelope and then formed one of Ilva's stripped stars, is now 100,000 Kelvin hot, and you don't see it in the wavelengths ranges which you look at anymore.
Right. So I think the issue that I run into when thinking of the scenario is that we can measure the total luminosity of the source from the current SED from JWST, and it's not clear to us like where is that luminosity going from the star. Like so in that process that you mentioned, would you expect a 10 to the 5 solar luminosity star to like?
Volumetric luminosity wouldn't change, but it would all go into the far UV.
Right. But where is that going? Because this source is currently this. So let's say even that if all of it is far UV, and we know that dust is completely opaque to far UV radiation.
Okay, then we do it isotopically and,
Right. Yeah, I think it has to be somewhat fine-tuned. Like the far UV radiation should be radiated by the dust shell, because dust is opaque to far UV, but you don't see that luminosity anywhere in the dust. I think that's the issue.
Kareem?
So when you look for these, a lot of them will have binary companions, and so they won't disappear completely. So with that in mind, can you speculate on the rate of failed supernovae and how it compares to regular supernovae?
Sorry, say that again. What about the companion and the rate?
So if it has a companion, it won't disappear completely. It'll just get fainter.
Yes,
so you don't find all of them. You only find the ones that have very faint companions, or you don't find them at all.
Right.
So now you have n equals 2. So you have a Poisson error of square root 2.
Yes.
So what's the rate?
I think like Ilva was saying, we are very much in the single object. Two of them. But turns out that, so obviously I don't want to go to the extent of estimating rate from M31 because it's a very nearby source. But we did this calculation. I don't think we've gone as far as estimating rates from this object. But turns out that if you take the results from the LBT survey, and I think they were finding like 10 to 40%, that's their estimate based on the number of successful and unsuccessful events they found. Turns out that those numbers, so yeah, I think 10 to 40% is enough, but I think we're still finding 1 in M31 over this 15-year baseline is lucky. I looked this up, turns out there is only one known supernova in M31, that was from 1885, and that was a type 1a, so spoiler. So we've actually never seen a core collapse supernova in M31 in all of human history. So the first one happens to be one of these guys. So I think, I don't want to do rates with this one object, but the LBT constraints are consistent with, I think we're estimating there was a probability of like 20% that we would see one in M31 over the course of 15 years.
Thanks, very nice talk. So if these stars really become black holes, and they probably have a natal kick, can you actually see them?
Right, so I guess from what I hear from my theorist friends, if you have a complete implosion, you don't expect a natal cake.
Okay.
Oh, well,
Adam.
okay, I'll let Adam speak. Yeah, small, yes. So,
Okay, how small it is,
yes.
like.
Right, I think the issue right now is that, I mean, the more common question I get asked all the time is what about X-rays if it's accreting into the source? We did this calculation. If you take this, 5 solar mass star and put it into the black hole, it turns out that it's going to be, it's continuing to be going to be very obscured for the next foreseeable future, like decades. So we were actually, with the JWST data, we can measure the column density of gas around the source, and that's like 10 to the 25.5 or something. It's huge. There's no way you would observe it, this source, in the X-rays. So I think until the black hole emerges as a naked object, there is no hope for directly detecting it, but maybe in a
century.
decade. Yeah, it's something. This is a very long time scale process.
So this is an accretion powered in the shell on the outside. Is the shell moving, and do you have a velocity measurement of expansion velocity rate? And at some point the dust presumably would be destroyed through this X-ray emission that's occurring in the center.
Right.
How fast does that occur?
Right, yeah, great point. So the picture is that the outer puffed up envelope of the star, which was originally 300 solar radius, is now falling back into this object. And so we have a high resolution JWST spectrum of the remnant. Turns out that I think because, I don't know, my guess is it's a fairly spherical implosion. I'm not going to guess because it's hard to tell, but from the JWST data, it's actually, there's no evidence for any bulk motions. It's kind of consistent, well, the lines are consistent with just the systemic velocity of the system in the disk of M31. So I think so what we are seeing is that there is a bunch of gas outside, and as the luminosity of the central source declines, more and more of it is going to condense into dust because the dust condensation radius decreases as the luminosity goes down for a source. So I actually haven't done that calculation if there's a point where the dust becomes less optically thick. All the models we are seeing is that because the luminosity is declining so quickly, you would expect just more and more of the gas to continue to condense into dust as the temperature falls below whatever 2000 Kelvin where dust condenses.
Yeah, I remember you saying yesterday during the coffee break that amateur astronomers also saw this star disappear.
Yeah.
I was wondering, could you say in magnitudes how bright this star was before the implosion?
In what? This was a 16th magnitude.
16th magnitude.
Yes.
Is that bright enough to be on like the old Harvard patrol plates?
Probably. I think the oldest record I found of this object was from the 70s. I don't know if, I was just looking up Vizier, all the catalogs on Vizier, but I haven't looked at the Harvard place specifically.
Yeah, I think that might be interesting because that might actually give you a 100-year baseline to look for these events in the very nearest galaxies instead of 15.
Yeah, right.
I mean, you obviously wouldn't see the mid-infrared flares, but
yeah. What was quite remarkable is that all the there are a lot of non-professional astronomers who look for novae in M31. And they have light curves, beautiful light curves of this source, but they were not looking for fading objects, looking for erupting objects.
And now with the smart telescopes, if another one of these things happens, there'll be thousands of people who have digital images sitting on a hard drive, and you just have to get access to them.
Yeah.
So you mentioned the cadence being very sort of
slow. Yes.
Slow.
Yes.
If you caught it in the act, is there something new you would learn that, what do you think?
No, yeah, absolutely. I think what would I not do to have an optical spectrum while the source was declining? So I think, we would expect quite drastic changes in things like so there are predictions for how the spectral type of the star changes as when you inject a certain low amount of energy into it, sort of puffs up for a bit and then it falls back. We would see beautiful evolution in the spectral type and radius of the source. Like here we're doing sort of everything based on photometry, but we know, the photometry calculations assume it's a, source in equilibrium, which is kind of the models that we have. But if you were able to actually spot the spectral change as it disappeared, that would be quite remarkable.
In one of the slides you had, it's a wind measurement of 10⁻⁻⁴.
Yeah.
Isn't that too high for what we expect for supergiants?
That's what I'm told. Yeah. Yes. So I think the 10⁻⁴ is a bit high, but so it depends on what type of supergiant we're talking about. So if you look at the population of yellow supergiants alone, which we know have lost a big part of their envelope, turns out that yellow supergiants systematically show very high wind mass loss rates. So there's this thing called supergiants, even hypergiants, depending on what part of the LT diagram they're in. But it's not unforeseen for yellow supergiants. For red supergiants, it's a bit high.
This is really interesting. So I think this method kind of, you have to be lucky and have archival data. Can you do anything with the Roman Space Telescope, or is that too blue in the near infrared?
Right. So actually, my personal opinion is that Roman is the next big thing for these type of searches, because with Roman, you would be able to see nearby, why is this like, you can basically see the local group, that's about it. And we have checked, there's no other stars in the local group that have done this. Otherwise, we would be a bit worried about the interpretation. But with Roman, you can essentially do this out to, I think it's similar. You can do it to the same depth as LSST, which is 50 megaparsec, but then you don't have to deal with the confusion, which is an absolute gain over there. So I'm pretty sure me or my colleagues will propose a nearby galaxy survey with Roman, and I think it has to happen. It's a no-brainer. So I think that's really likely the next discovery stream for these things.
Okay, let's thank the Kishalay very much again for a wonderful talk, and see everybody back here in 25 minutes at 11 o'clock. Thanks.